here on the Zoom call. And if I may, it would be wonderful to take a screenshot just to kind of put it out on our social media and say, look, we're actually, something's actually happening. So if you don't want to be in this, do please turn off your camera now. But otherwise, if you don't mind, I'll just quickly take a screenshot. You can put on your best smiles. Wonderful. Thank you so much. So welcome, welcome, welcome. It feels like this is a very long time in coming. I'm so sorry that you're not in the building right this second. As you see, I am in the building. There's maths on the blackboards behind me. But it will happen, and we can't wait to welcome you here in a little bit over a year. And in the interim, it's fantastic that we can keep the momentum going and have bridging workshops. And really, we just want to thank the organizers and the entire community for your patience and understanding as we've been trying to figure out how best to juggle things. The analogy that I've been giving is it's like we are air traffic controllers, and I has had a whole load of large jumbo jet programs waiting to land, and it's just been a question of knowing when we have the right runways available at the right times. And so we can't wait to have you actually landing this aeroplane, but it's lovely to see you here on Zoom in the interim. It looks to be a fantastic program that's put together for this workshop. And so that's going to be all I'm going to say from me. Just can't wait to have you all actually in the building, and I'm looking forward to ducking in and out. I won't be able to sit in on all of this, I'm afraid, but I will be ducking in and out during the course of the week. So have lots of fun, and I shall hand over to the organisers now.
Thanks a lot, Christy, for that. So I will be chairing the first session. So let me also, we are a little bit early yet, so I will just say a few words before we kickstart with the talks. So indeed, this is a bridging event in the sense that we have this program that has been postponed and will happen next summer. And we hope to put some more info on that towards the end of this workshop. But it's also a kind of a bridging event in the sense that it's bridging between math and physics. So we have, both mathematicians and theoretical physicists, both in the audience and in the speaker list. So it's a little bit unusual in that sense, and we hope that the speakers, at least to some extent, will be able to reach to the other side and create some new ideas and maybe fostering some research projects that could maybe happen in the next program, because of course we want to be in the same room and we want to talk to each other. So a few details also concerning this week. So we have 2 informal discussion sessions that are scheduled after the last talk today, so after Jens Funke's talk, and then at the same time on Wednesday. And these are intended just to give the possibility of chatting a bit amongst each other. And so there will be breakout rooms, but there will be no formal moderation on our part, but we will let participants go in and out of these rooms as they please. And we hope that as many as possible of the speakers will be able to spend a little bit of time in this discussion and allowing people to ask follow-up questions and so on. But otherwise it's completely free, so you can just go and see who is in the room, and if there is need, you can just tell one of us who is organizing, and we can create more Zoom rooms if that's necessary. But we will start with 5 and then we'll take it from there. We will also try to have a format where we allow participants to simply unmute themselves and ask questions directly to the speakers. We hope that this will work fine. Of course, you can also ask questions in the chat or after the talk, but we'd like to try to have somewhat informal setting where you can ask directly. If there are too many questions, then the chairman will step in and ask to postpone, but we'll see what happens. So the talks are 1 hour in total, which should include questions. So we ask the speakers to prepare 45 to 50-minute talks and then allow for some questions at the end. There are some more important things that we have to remember, and it's that the talks will be recorded, at least most of them. And that means that anyone who unmutes themselves and asks a question is automatically allowing us to record you. So unless you want to be recorded asking a question, then you'd have to pose your question in the chat or wait until the discussion session. Because basically these lectures will end up on the Institute's YouTube channel fairly soon after the talks. And then, as I understand it, a little bit later, I don't know, a week or two later, there will also be edited versions on the Newton Institute website. So just remember that. Then there's one final thing that I should say to all the participants listening, that you see at the bottom, there is a little live transcript icon, and that will be very helpful for some people. But if you find that a little bit annoying, you can just click that and you can turn it off, but it will be on otherwise, as I understand it. So I think that's all the details, and we will wait a few more minutes before we start with the first speaker. Steve, maybe you could actually start now sharing your screen and prepare. Thanks all. Okay, so now it's time, and so we welcome everyone to this Newton Institute workshop, New Connections in Number Theory and Physics. So this is, as we mentioned, a bridging event which is connected to the program that will happen next year. And we are very happy to welcome our first speaker today, Steve Miller from Rutgers University, who will tell us about sort of a new perspective on some interesting old functions coming from string theory. So please, Steve, take it away.
Okay, well, thank you for calling them interesting, so I don't have to. So I want to, basically, I want to talk about things related to work I did with Michael Green and Pierre Vanhove, and the timing is perfect for me because Saturday actually was, oh, it's not working. Saturday was actually Michael's birthday. So this is in public domain, so I can say it. So Michael and many of his collaborators, I mean, this only one collaborator is in the picture. As far as I know, he never worked with the cows or the people punting, you know, in the background here. Did very interesting work starting at least in the 90s on automorphic functions. And it was really amazing luck that I was able to be involved with them, luck for me, starting in 2009. And this to me, I mean, the types of questions they ask are a really good example of how ideas from another area can really influence mathematics. So the thing is, if you go to look up Professor Green, the famous Lucasian professor, online, you may find, as he's done, that you find the wrong person. So he's apparently famous for more than just string theory, and but it happens to be, yes, Michael introduced me, or at least told me a lot about the cicadas in Princeton that he just barely missed as a postdoc. This is now the week or so that they're out again. Every 17 years they're out. And of course, there's another person who combined electricity and strings and sang about the cicadas, whose birthday is also today. Anyway, let's get back to physics. So Michael and Pierre and other collaborators were studying a very basic question in physics, namely what happens when two particles interact with each other. And in string theory, it's very interesting to look at the graviton. The graviton for the mathematicians is a hypothetical particle that's supposed to transmit the force of gravity. No one's ever actually seen one directly. I mean, you may argue you've seen billions of them, but to actually the individual level, this is something theoretical. And the only type of laboratory that you can use to study this at times is mathematics. And so in a way, this talk is about what happens in that laboratory of mathematics in studying this. So this is in a asserted model of string theory. It's maximally symmetric. It's type 2b. They're Detroitally compactified. Okay, so Bob Dylan has spoken about gravity. So here's a picture that you have two gravitons coming in, and they, you know, if they don't interact, it's not interesting. So here they are smashing each other up, and then afterwards, two guys come out. And then the question is, how are they coming out? What direction are they scattered in? It's quantum mechanical, so there's a probability distribution. And so this is, of course, something that's gone back a long time. The new twist on this is that there's certain parameters in the background in string theory on which there's an automorphic dependence. So I'm going to try and separate out the Riemannian geometry, which of course goes back, early last century, to some more fine-tuned things that happen at low energy scales, for example. Okay, so that's kind of the upshot. There's some coefficients that govern these interactions. These coefficients are not seen without string theory. So already, I guess that makes it interesting to see how two theories compare. And then for the mathematics, the automorphic coefficients are very interesting functions at times. Okay, so let me say a little bit more about this to be technical. The scattering amplitude is usually separated into an analytic, a non-analytic part. I'm basically only going to talk about the analytic part. And then going back to general relativity, there's an expansion that's written in terms of momenta. That's what it looks like, something like a power series. So maybe not to say too much about what this means if you haven't seen it, but this first term here is general relativity in some sense. This is the Einstein-Hilbert term. It's a contraction of 4 Ricci tensors. And then string theory predicts there are these low energy correction terms that have a dependence, I guess a field dependence on this parameter phi, which I'll describe in a moment. Okay, and these will be the automorphic coefficients. And then these low energy terms, these momenta, you'll see something like terms like d to the 4, r to the 4. These Mandelstam invariants are momenta, but you think of them as differential operators. Okay, so going back even before string theory to the work of Kremer and Julia in the 1970s, there was an important notion introduced that these phi sub d plus 1, d is the dimension here of the physics involved. They naturally lie inside a symmetric space, and it's a symmetric space for one of the exceptional groups usually, or at least a certain or a subgroup of them. I'll put a table up in a second of what those are. And in string theory, though, there's something more important. These things don't just live in a symmetric space, but they're invariant under a discrete subgroup. And this goes back to ideas of Dirac about quantization. It's referred to. This also comes up in U-duality. I don't want to say too much about that, but it's a very deep idea that it comes in. It's not just put there for decoration. And so the big problem is, what are these coefficients? This is a completely fundamental problem, I think, in string theory. You have one of the most basic questions you can ask. You have gravitons interacting, and the nuance between this and other theories is that there's some interesting dependence here. And so what is it? Okay, so here's a table, by the way, of these groups ED. You just take the Dinkin diagram the way it's usually numbered and lop off nodes from the right. I keep forgetting to change this. This is spin 5,5, not SO5,5. So these are all, you can think of these groups that they're all the real points of the simply connected Chevalier group. Okay. And as the tower goes down, you get down to SL2. There's some funny things that happen in this direction. And then you could imagine you have a lower dimensional space and then start talking about E9, but I'm not going to do that here. All right. So the Eisenstein series showed up quickly, and this was understood by Michael and Pierre and other collaborators, I think, for SL2. And then we had a very long project to try and identify what these correction terms are in general for higher rank groups, and they are also Eisenstein series. So I don't want to, time is short, so I'll avoid a technical definition, but one way to think of it, in some cases, it's the same as what's called the Epstein zeta function of a lattice. That means you take all the non-zero norms of vectors in that lattice, and you sum it up kind of like the Riemann zeta function. I mean, there's a normalization of it too here, and this converges in a right half plane that has a continuation, and the values at points where it doesn't converge, but where it makes sense by continuation, are giving in many cases these coefficients. Okay, so if you haven't seen this, you've seen this for one dimension because it's the Riemann zeta function at 2s. In 2 dimensions, Siegel introduced these non-holomorphic Eisenstein series. It's worth just spending a little time on this. Eisenstein himself looked at the series of CZ plus D without absolute value, just parentheses, to an integer power. And this is a non-holomorphic version. It's just the imaginary part of gamma of Z. Z is x plus iy, and gamma is some matrix A, B, C, D. And then there's a normalization on the outside. And what's very crucial is to understand the Fourier expansion, because this tells you the asymptotics. And the asymptotics are presented in ways that have perturbative terms and these instanton terms. These terms integrate out when you integrate x from 0 to 1. And there are already a lot of ideas coming from string theory about how to understand this in special cases. So the divisor functions come up in terms of wrapping around branes and things like that. Okay. So here's the answer for what the coefficients are in the first few cases. I'm not doing the Einstein-Hilbert term because then it's a constant dependence, and that's been known for a long time. And so let me show the table. There's a bunch of Eisenstein series here in the table, but what I want to draw your attention to is if you start from SL2Z to the work that Michael, Pierre, and others started with, they had a 3/2 Eisenstein series and 5/2 Eisenstein series as on the previous page. That's the value of S. So at 3/2 and 5/2 here, this is what occurred for SL2Z. And then in higher rank, at the top very end of this table, it's also the exact same pattern. It's just you have to, it's something called a maximal parabolic. I don't want to go into that in detail. In the middle, the answer is very complicated, but there is really, it's striking how this answer of 3/2 and 5/2 wants to come out exactly in all these cases. So these are points where a series doesn't converge, it analytically continues, or you could think of it as a residue at some other point, but it's really striking there's a general pattern. And this general pattern I think is very important for the mathematics I'm going to talk about later when I talk about Arthur's conjectures. This helped lead to a proof of many cases. So how is this understood? Well, the basic idea here, I think it's worth mentioning. If you take here you have space-time that's compactified up to 10 dimensions. You have certain dimensions involved, and you're compactifying by a torus. Now, that torus might be might have very small radii to it. But if one of those radii was very, 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 very large, you really wouldn't be able to tell that that was an infinite non-compact direction or just a compact direction. I mean, for all we know, every dimension we're in now is compact, right? We have no idea. We can't see that far. So in doing so, then there's some understanding of how these functions behave with respect to that change. And that gives really important information because it tells something about the asymptotics of these functions. That's the crucial information, is to understand their asymptotics. That will also be crucial for Arthur's conjectures in a moment. So there's a very deep idea that came from string theory here from this comparison.
Quick question, Steve.
Sure.
When you have a sum of two Eisenstein series here, is there some relationship between the parameters?
So here, like in SO55, so yeah, probably no one can see it. There's a little hat over it. So what happens here is that there are two different series that had to be added up, and they both have poles, and the poles cancel. And this makes sense by regularization. So I'm not trying to understand exactly your question, but there were certainly. Maybe you could say it again. I'm not sure I got what you meant.
Oh, we can talk about it later. It's not important.
Oh, my pleasure. Okay. Another important thing about these interactions, at least the first few that we identified, this is again crucial, is that there are differential equations in the background. So here it's a good time to review a very important distinction between that of automorphic form and of automorphic function. An automorphic function just means it's invariant under a group. An automorphic form it's a more robust definition that requires differential equations in the background. So for example, I mean, you can ignore these delta functions and just make them 0. The first two interactions that I looked at are here, and they satisfy Laplace equations cleanly. They're annihilated by Laplacian, they're minus a constant, so they're eigenfunctions of a Laplace operator and many other differential operators. They're automorphic forms. They're Eisenstein series. But after that, the equations get very interesting and very complicated. And this is a good example. Will come up again towards the end of the talk. Here you take the Laplacian minus a constant on this other guy, and what you get back is the negative of the square of the first one. That's not the type of equation we see very often in number theory, if at all. And it's representative, I believe, of many other ones which would be very important to solve and understand. So in a way, the understanding of these correction terms is really limited by the fact that the objects themselves they kind of leave number theory in a way. This also goes under the name of BPS protection. There are BPS states with different amounts of symmetry and so forth. So the last one doesn't satisfy this type of equation, so it's not an automorphic form, which makes it I mean, it's still interesting to study, but it doesn't follow, it doesn't fit into Langland's picture cleanly, for example. The other two do. This is the differential equation for SL2Z. You take the 3S Eisenstein series, square it. Maybe I left out a sign. And to get this solution, you want to invert Laplacian minus 12. It's not hard to see there are solutions, but to study them in detail, as we'll do later, is not immediately apparent. Okay, so
can you say, Steve, anything about the representation theoretic nature of what's going on? Are these non-semi-simple representations that are coming in, or infinite integrals?
Well, I just don't know, but there have been a number of suggestions, which I'll touch on, that they are related to small orbits. But I just don't, I myself have never understood that. If you expand, you can spectrally expand this in terms of the automorphic spectrum, and you see basically everything in the automorphic spectrum. So it's not precise enough to narrow something down, unfortunately.
Thanks.
Okay. All right. So there's a whole series of other functions waiting to be uncovered, but I mean, I don't even know how you would know if you had the right answer at this point. We don't understand the differential equations well enough to do that. So what I mentioned before had to do with asymptotics, and that has to do with what are called instantons, perturbative terms. And now there are, and so some of them are also not perturbative, but now I want to discuss things that don't have to do with the asymptotics directly, but have to do with the Fourier expansion. They're called instantons since they integrate out. So I'll just throw through some terminology here, probably, sacrificing some clarity. Here, one wants to take a maximal parabolic and look at its decomposition as a reductive group L, which is usually just one of these smaller groups in the table, and U is its unipotent radical. And usually this is, in the cases you look at, it's abelian. And the discrete subgroup of that these functions are invariant under intersects U basically in a lattice. It would look very much like Z to the N usually. And so we want to now do Fourier theory over it. So what you do is you take a character, this multiplicative group, and you make it trivial on these integral points. It's like e to the 2 pi I Z, something like that. And then you just integrate against it. And this is how you define a Fourier coefficient. And that's enough to reconstruct the function when this unipotent radical is abelian. But in many cases, like on E8, it's never abelian. So instead, you recover just a little piece of it. And then, of course, you might want to keep digging and look further into that. And there's been a lot of work in that direction. So these pieces are important because when there's BPS protection, there tend to also not be very many of these coefficients that are non-zero. So one ideally would like to compute them and understand their asymptotics, but it's just even show that the ones that are supposed to be zero are zero is an interesting question in itself. There is an action of the group L. So this function is automorphic under L. And if you dive through and move to swap the variables around and change things the obvious way, you see that some of the characters are related to each other by this action of L. And so there's a notion of a character variety. This is called an internal Chevalier module in some cases. You have sort of different pieces, and some of them are more complicated than others. And that's going to come up shortly. In fact, right now. So I'm now going to tell you the theorem that explains this for the interactions on E6, E7, and E8. Okay, so this maybe is not presented ideally, but I'll try and see if I can get this across. The point of this theorem is to prove a prediction made from string theory. So if it didn't come out this way, that would be bad, right? So that we look at these first three terms in the low energy expansion. So there's the constant term, the Einstein-Hilbert term. And then the other two terms are called E00 and E10. And this is for the force scattering amplitude as before on E6, E7, and E8. So the theorem before was that these are Eisenstein series specialized at certain points. I didn't mention this S equals 0 before, but that's just getting the constant function from an Eisenstein series. It's not deep. And now we'll look at 3 different parabolic subgroups. These correspond to the 3 extremal nodes of the Dinkin diagram. And we can try to look at Fourier expansions in these. And so the first statement I'll make, which is obvious, is that the Fourier series for the constant function only involves 1 coefficient. I mean, duh, it's constant, right? So only the smallest of these character variety orbits will come up, namely the trivial orbit. So now we can look at the next term, which we expect to be a little bit more complicated. And again, this was a statement coming from understood in terms of physics, and it was actually verified by mathematicians earlier, by Ginsburg, Rallis, and Sudry. Here you have more than just the constant, but you don't get much more. You just get 1 more character, and it's sort of the orbit carved out by it. And now the new theorem was the next term has what you might imagine, the 3 smallest orbits appear, but nothing else appears. But this seems to break down immediately after it. At least if you say it this way. So this is it's always fun to have a chance to verify a prediction using different tools. But this was the launching point for a connection with representation theory that I want to now turn to. I should also say that it's more than you get much more than this. You can also predict the asymptotics of the non-vanishing terms that occur. There aren't that many, and this is something that, I mean, can start listing names, but many people have been studying this and found that the string predictions work out. Okay, so here's the connection to representation theory. And so there were some ideas, certainly, I should acknowledge, certainly Boris Pielin and Unitsky had, I know they had some ideas in this direction before. So the right way, as I understand it, to handle that statement in the previous page is to use representation theory. And you need more than just the one interaction to really understand this. So there's a notion of automorphic representation. What that means is you look at functions on G invariant under gamma, so all the automorphic functions, and you impose some growth condition like L2. That's good. And then the group G acts by right translation on the functions. So you haven't messed it up on the left. So you still have something automorphic. And then this space just reduces tremendously into all these interesting pieces when you do that. And so you will look at the piece corresponding to one of these Eisenstein series. Now, of course, that's not an L2, so you have to be a little careful how you, well, actually it will be an L2. That's the trick, but you have to be careful about how you set this up. One way to think of it is you take the thing you're interested in and just keep acting with right translates and take linear combinations and do that, and take limits, things like that. So the objects themselves have a representation theoretic statement, but it only goes so far. You need to also relate the Fourier coefficients. But that actually works out fine because the integral defining them is just by inspection. It's a linear functional. And if you translate on the right, it doesn't affect the integration on the left. So you can put fancy words in front of it, but there just aren't that many. It turns out to be a type of object which is pretty rigid and well understood. So there are a number of theorems of the type that say if a representation isn't very complicated, it's not smart enough to have interesting linear functionals. The great example is the trivial representation. There's no interesting linear functionals on it. And these other representations, being what we call small, as we'll see in a moment, also don't have that many interesting linear functionals. So there's a whole theory, I meant to pull it out as a prop. Adams, Barbash, and Vogan have an important book from, I guess, around 1988, 1989 or so. I think it was published in 91 about Arthur's conjectures. And there they did a lot of work proving very interesting theorems about this thing called a wavefront set of a representation that measures its size. And it takes some work for someone to, well, it took me a lot of work because I had no idea what any of this stuff was, but for students of those people and those people themselves, it's very easy to just write down the right statements, and it works out perfectly. This statement that Adams, Barbash, and Vogan have proven with a little bit of work just very cleanly gives this instanton vanishing that was predicted by string theory. So another way to say it is that these interactions that physics is identifying are automorphic realizations of interesting representations, and that in itself is not an obvious thing you can go around doing. I mean, this is the type of thing people have been writing papers about. So it's nice when nature, I just wanted to distinguish, it's very important when there's an application in another area, whether that application comes organically from the other area or not. And here it clearly did, just right, it just handed to in a way. So let me skip some details of that. Okay, so there is a connection with representation theory. It's useful for proving a lot of coefficients are zero. It's also useful for computing the coefficients when they're non-zero. And I now want to turn to things that maybe where the technology transfer starts to now run in the other direction, where the ideas from physics now can help prove things about math problems. Okay, so just to maybe get back to the big picture, we've identified some interesting automorphic forms that come from this low energy expansion. And in a way, you can think of them as being like the theta function. This is the first modular form ever discovered. It's a Jacobi's theta function. This doesn't have that many interesting Fourier coefficients. They're mostly zero unless you're at a square. So that's kind of a similar idea. That otherwise, there's really no way to see these phenomena for SL2 or even SLN. They're things that are really exotic that happen for exceptional groups for the most part. And so there's been a lot of study actually of the R to the 4 interaction. That was the first of the non-trivial ones. It's the minimal representation, the study by Kajdan, for example. And that automorphic realization had a lot of applications to number theory. So it's been used for theta lifts. It's been used to make very interesting L functions by integral representations. This was all done before physics had kind of publicly identified this thing. But in a way, that's just a coincidence because the problem of graviton scattering is natural enough that one day or another, someone would have discovered that these coefficients are there. So what that tells us is that there's tremendous power in these ideas from string theory to find objects we mathematicians don't necessarily see easily. So that hasn't necessarily happened yet because here they were seen first, maybe not easily, but they were, there's very deep work that had gone into that. But there is the potential there. And I think that potential itself justifies this type of exploration. Because frankly, I mean, really big progress in math usually, I shouldn't say usually, but very often happens when outside ideas are interjected. And this is a place where there might be more good outside ideas, we hope. Okay, so that third term in the expansion is the next to minimal representation. And you would think this would keep going, but it just doesn't. It just seems to stop here. Now, one area where it might keep going is that you don't have to look at gravitons, you don't have to look at four particles, you could look at all sorts of other interesting particle scattering amplitudes, and that you could also relax the type 2b. You could look at some other compactifications. There's some work going on with that. Okay, all right. So now let me come to some of David Vogan's picture is still on my screen, so we can talk about this. Okay, so here's a picture, by the way, of, I was mentioning orbits. These orbits, I didn't give a definition. They're orbits on a complex Lie algebra. They're nilpotent, and they're orbits of the group acting on the Lie algebra. So it's a generalization of Jordan canonical form. And here's a picture Jeff Adams made. I'm supposed to attribute everything here because I signed a copyright form. So there are all these terms that arise. So these first three terms here are the ones I've been talking about. And the one after it, well, this may not be labeled appropriately. I'm not sure. We think one of these other orbits somewhere around here might be related to the next type of term that we don't understand yet. But this picture is very tempting because it's clearly telling us something important about the scattering amplitudes. It showed up so cleanly in these answers. So David wrote this a few years ago, which I just have here just to have independent authority of the importance of looking at the representations attached to these orbits. This was a huge industry here. So just to back up, I mean, it's right here. These are the same Eisenstein series that have appeared, basically, at least in special cases, and what I've talked about so far. So there's a whole subject here within representation theory of trying to create interesting unitary automorphic representations that are difficult to construct in any other way. So this falls under the rubric of the unitary dual problem. This is one of the, I mean, I'm quoting Wilfried Schmidt here. Well, I haven't heard anyone disagree with this statement that this is the really hard problem that remains in representation theory of real reductive groups. So it's the headlining problem. And among that, this problem is a very, very subtle problem and intricate, but there's a very natural class of representations to look at there. And these are called Arthur's uniponent representations. So I'll spend a few minutes now to discuss that. And the relevance is that in the cases discussed so far, the representations are in fact of the type that Arthur is conjecturing. So now we're moving in a direction where something computationally and theoretically worked well from the point of view of physics matching up with math. And we want to see what other math can be discovered using those ideas and the insights coming from string theory. Okay. So for example, very basic questions, can we make automorphic forms for all these other orbits? Or can we even identify, very basic question, what are the representations? So Arthur's conjectures are stated in you might say, an indirect way, that a class of representations has properties, but can you actually list them explicitly in a table that someone could work with and do computations with, for example? Okay, so the unitary dual problem, just to be more precise, it's simply you want to identify all the unitary representations of a Lie group. We know in a sense what all the representations are, but it's not obvious which ones have positive, definite, and invariant Hermitian forms. And the way a representation is handed to you, it might be obvious it does, or it might, but it might not be. So this is something that really, the understanding of it really depends on having different models of the representations. So if string theory can give us different models, that's also useful sometimes. So I don't even want to begin to show you what it looks like for some small examples, because it's very hard. This has been worked out for many cases like SLN and G2 by David Vogan, and complex classical groups by Dan Barbosh. And maybe I'll stop the list there because there's a few other cases, but it's certainly, there isn't even a conjecture of what the answer looks like, say for E8 that's precise. Okay. So there is, however, a beachhead case, you might say, these Arthur ones, and they come from Arthur's more general conjectures about automorphic forms. They have to do with realizations as, say, cusp forms or as Eisenstein residues. But there have been some statements floating around that these are kind of building blocks of the unitary dual. I think those statements are not precise enough to be useful or correct, if they are precise enough. But I think it's well agreed that this is. I mean, put it this way: I haven't seen anyone come up with a list of other cases that are supposed to be harder than this, but I can be corrected if I'm wrong. I mean, no one knows cases that are harder. Computers we're ignorant. Let me see how we're doing with time.
You have basically 30 minutes. You're half time, Steve.
Am I supposed to stop 10 minutes early, I think, right?
Yeah, so that's right. So you have about 20 minutes, and then we
Not to mention that I have to run to the pediatrician.
Okay. Yeah.
Okay. Let me just give a few definitions. So the complex points of Langland's dual group enter here, as they of course did early on in string theory, and this was part of the exciting motivation for geometric Langlands being studied by string theorists. There's an important group that comes up in classifying representations called the Weil group. It's easiest for me to think of it as some subset of the quaternions. This is the usual IJK. And then an Arthur parameter is an interesting object that, I mean, in a way you could phrase it completely without representation theory, but it's very natural to describe it this way. It's a map from a product of two groups, a direct product of SL2C and this Weil group, and it goes into the complex group here, and has to satisfy various properties. One of them I'm not even going to mention because it becomes nullified by what I'm about to say next. We're going to look at uniponent Arthur parameters, and here that the Weil group part just breaks down because it will be trivial on C star, so it just depends on what it does on J. And J squared is -1, so it's got to be trivial on that. So psi of J has order 1 or 2. And then to be a homomorphism, you need the image of the SL2C to commute with this. And that in a way, that's kind of telling you what's going on here is you have an order 2 element, and then you look for things that commute with it. And there's a central algebra, symmetric algebra, it stabilizes. So it's the idea of David Vogan to enumerate the psi of J's, and then the orbits, the uniponent elements here come in orbits that parameterize these. So you can make a list of these. I mean, Joe Henley and I did for the exceptional groups. There's 341 of them. What does it mean, though? Well, there's a few different ways people think of it. This is useful because it's literally true in certain cases, but literally false in other cases. the SL2C is kind of telling you away how far the representation is from being tempered, but there are cases where this is non-trivial and yet the representation is tempered anyhow. So that's a subtlety. Another way to say it is that it has to do with the size of the representation, as in the sense I was describing before. So in a way, how smart it is in terms of affording to have, or how rich it is that it can afford to have interesting non-trivial linear functionals. That's a whole other direction here, but I just wanted to give some intuition that for every way you can stick an SL2C into this dual group, and you have this order 2 element in the background also, you can start talking about different sizes of representations. And it's sort of order reversing. So the trivial representation doesn't come from the trivial map here. It comes from the one with sort of like, in a way, the largest image, you might say. That's not the right way to say it, but I did. Okay. It's like, this is basically these orbits again are like Jordan, these SL2Cs are like looking at nilpotent orbits, which is like Jordan canonical form. So the trivial orbit would come, I guess, from the largest Jordan block. Okay, so now those are the parameters. So this is something you could, in principle, compute. You have to do it the right way, or else it drives you crazy. My screen is blinking. I don't know.
Everything looks good from here. So
I don't know. This is like in a movie where like the radio signal's dying out. Okay, maybe it just wants me to keep talking more. Now it's black. All right, I'm seeing half the screen in space time, and okay. So
we're seeing your slide. There seems to be
okay.
No problem.
All right, so I'm going to be. If you see my eyes are blinking, it's just to being out of sync. So that okay. Arthur predicts a packet of interesting unitary representations for each of these parameters, and in fact, the packets can overlap. So that's not great for making lists sometimes. But so the question is, how do you define the packet? And so Arthur's definition gives some properties they satisfy, but it was really, I think it's fair to say, Adams, Barbash, and Vogan gave a workable definition. I mean, there's various nuances in this that David will correct me on again, because I would keep getting it wrong. But for at least for real groups, there is a definition that one can give, but that still doesn't tell you what they are. So there's one element you can describe in each of these packets, and that's one that you can very cleanly make from the parameter. I don't want to go into the discussion of that, but it's a way you make a principal series with like some signs based on what psi of j is, so that the orbit tells you what the infinitesimal character is, the representation, and there's a non-trivial part with it, like order 2 elements tell you how to induce it. Okay, but there's a notion which is just as good if you want to study unitarity, which is the notion of weak packet. And that's what you do is here, you just take a whole bunch of these packets together if they have similar information, namely if they correspond to the same orbit. So you could describe this as that this is for each orbit, you can define an infinitesimal character and a wavefront set if you say it the right way. And this is all, the easiest way to say what this is that this is all the representations that have that infinitesimal character and this size, you might say. So there is software that many people have worked on called Atlas software. And I've been doing a lot of joint work with this group I'll mention on the next slide to compute what the representations are. The screen is now completely black. I mean, I wish I could take a video to show you what it looks like here. It's I guess I could log in with another one on my phone and show you, but it's blinking about 6 times a second and showing green and all sorts of weird colors. Not Michael Green. Okay.
It sounds like a Zoom. Sounds like a Zoom bomb.
Really?
Yeah.
Well, okay. All right. Maybe I will take a video just to someone wants me to prove it to them later. Okay. So Arthur did a lot of work on these conjectures, and his book is a real monument. And in that book, he settles very hard cases that are for classical groups. Now, classical group for him doesn't include spin, and so we won't have a complete statement here because we can't touch the spin groups, but he's looking at the split groups, and other people generalize to quasi-split. And I should say that Adams, Barbash, and Vogan basically understood, as far as I understand, all the properties that one would want from the conjectures of these representations, aside from identifying them explicitly, and the big one is unitarity. And unitarity, of course, gets easier the further you get away from split, because every representation of a compact group is unitary, at least every irreducible, I guess, or is unitarizable, I should say. Okay, but the classical group situation is really different than the exceptional situation, because a very important object in understanding this is the component group of the image, the centralizer of the SL2 image. That's always an abelian group. For exceptional groups, it's going to be pretty exotic. You can get S5s. So the representation theory of that S5 has to come into this in terms of understanding what the packets are. Okay, so Joe Hunley and I investigated these elements that Arthur explicitly wrote down. They're called Langland's elements. And we used Eisenstein methods that were, certainly in a way disjoint from what I had done with Michael and Pierre, but certainly you could say like they're offspring in a way. It's much more complicated because they're intertwining operators. In a way, that's the intertwining operators are the whole story there. The other cases, we're looking at spherical representations, which were more combinatorial. But this has been completed, and now each one of these Arthur representations has been shown to be unitary. So what you could say here is that aside from the spin groups, which Arthur comes close to covering, every representation that he explicitly conjectured is unitary. And that's using number theoretic methods that come basically directly as offspring of ideas from string theory. But I'll go a step further now. So recently, Jeff Adams, Marc van Leeuwen, and David Vogan and I spent a lot of time trying to work out what the ones are that Arthur doesn't specify. And we have created a list of these. I'll show you something on the next page. And now, just as a few months ago, we actually have now also shown they're all unitary as well. So this proves, this settles the question that had been studied for, I guess, since the late 80s of showing the unitarity of the Arthur representations for real exceptional groups. That's almost the whole picture because, as I mentioned, the classical group case is in very good shape. But strictly speaking, one would have to go back and look at different forms of spin groups and things like that to finish it off. But I think it's pretty clear the hardest cases have been understood because Arthur's work in the classical setting did the hardest cases, I think, or very close to it. I mean, I think that it's not even clear there are that many cases beyond what he did. And the exceptional case, they're all completely handled now. Okay. So some of these packets are, the reason I'm mentioning it here in this conference is because these representations probably are the harmonic analysis relevant to studying some of these other orbits. I mean, they were in the cases we looked at so far. So the packets have representations that we just don't see very easily. They're it'd be interesting if string theory can identify them. The ones that people have studied so far tend to be singleton packets where there's only the Langland's element, none of the other ones that are more indirectly part of it. Okay. And it'd be interesting to make automorphic realizations of it. The methods that we've been using, and David, Jeff, and Mark, those have been methods which are more internal to representation theory, aside from one example where we tried to use an Eisenstein series, but later could do it without an Eisenstein series anyhow. Okay. All right. So here is there's a list of them. There's about 1,500 representations here. I mean, so for E8, there's 362, whereas only 3 of them have been studied so far, really. And it could very well be that some of these are relevant to other phenomena in string theory. I don't see why not. I mean, the first 3 were. These aren't that different in many ways. Okay, so just the upshot is that, just to summarize it, that these small orbits and small nilpotent orbits have to do with the leading terms in the graviton expansion. And now we've understood the full class of these representations. I think it's fair to say, and in the sense that we've written, maybe understand is not the right word. We've identified them and shown they're unitary. Okay, so now the rest of the talk, I want to talk about these higher terms that don't have anything to do with representation theory directly. I mentioned before there's been work about identifying them to higher orbits and higher rank groups, but I'm actually not going to say anything about that here because I just have nothing to say. Okay. All right, so this next term is really interesting. And in fact, it was at the Newton Institute that we worked so hard on this. This is the term that's defined by this inhomogeneous differential equation. And what one would like is to write it. I mean, it's not hard to show it exists in the sense that we were able to do that many years ago, but we want to show that it has a Fourier expansion of a certain type. And when I've written it in the screen, you see on the toward the side, I can see my own cursor now through the phone. You see here, this is organized in a way that's very useful in terms of understanding instanton vanishing. And it's sort of paired up directly against what one would get if you took the Eisenstein series, squared it, or took the Fourier expansion and squared it, you would get terms of this mixed type. Okay. So let's see. All right, so we actually solved, this is one of these things where you want to solve the problem the worst possible way, and boy, did we ever. We actually just guessed the answer. And in case you want to see, this is the guess, but you don't want to see the guess. This is a mess. There was no, really what I want to describe is there some organized way which one might arrive at the complicated answer here without resorting to guesswork after many frustrating years of trying to understand it. And just to put something more humane on the screen, here's really what the solution looks like. It's a sum of a bunch of different terms. I want to highlight to you what they are. So the term delta, the delta function here, this is just the constant term. And these other terms here, I should have said it, this only comes up when n is non-zero. It's some multiple of the Bessel function. And then there's a bunch of other terms that are bilinear in Bessel functions with some ugly polynomials. I mean, it's not that bad. The whole solution was on the previous slide, but it doesn't have any conceptual thing that, you know, a mathematician might call beautiful or anything like that. So there's two big questions here that remain even after we guessed the solution and verified it had all the properties we wanted it to have. Namely, where does it come from? And how could you actually construct this without guessing? That's important because there are many other differential equations of this type that have come up in this theory. They also come up in modular graphs functions. And you don't want to have to rely to guessing it. You want some method which produces a solution to an equation like this. And the second one, which was very striking to me, is that Michael and his collaborators have pointed out that it seems likely to be the case that this term just shouldn't be there. That coefficient alpha n should be 0. Now, we didn't see that because alpha n arises as a sum of an infinite sum from other terms, these n1, n2 terms I had mentioned before. And it really does come up for each of those terms, but it seems to cancel out. And that's something that's very hard to see. That's some long expression in terms of divisor functions. So some infinite sum of shifted, like a shifted convolution sum that's 0. And I don't see any way to handle that easily using mathematics, I know. So I want to quickly get into this, and you'll cut me off when you need to. There is now a solution to both of these. So Kim Klinger-Logan, I'm sorry, this isn't going to fit on the screen, but Kim Klinger-Logan and I have made a method that derives a solution, and it's picking up from where Michael, Pierre, and I left off. There were some ideas of Don Zagier. I'm not sure what his role is, but there's an arctangent off the side of the page here. I want to explain what the idea here is that it's something Pierre and Michael and I had tried to do, but failed, is we try and write down the square of the Eisenstein series and just make a differential equation term by term that matches it. And we look for a solution of a particular form. You might say it's A invariant, where A is diagonal matrices acting on SL2R. And so that differential equation is right there on the left, and the solution is on the top somewhere. Again, I can't see a pointer. And so if you can solve that, everything converges nicely, and you'd be able to sum it up. But the problem is that there's an integral that we just couldn't do. We tried very hard to do it. And there is the integral. So Michael came to visit me to work on it, but the kid who came in earlier was born the next day. So anyway, but we still, even that wouldn't have made us able to do it anyway. So there's a hard integral to do. And what makes it hard is that there's an arctangent. So now I want to come back to the real birthday boy, is that I want to point out to you that the arctangent, if you consider a certain differential operator to be a death, and this arctangent to be an evil judge, that Bob Dylan's statement is not right. Okay, so this integral determines the coefficient very easily, and namely, oh, the gag didn't come up. Did it? Do you see Dylan? I can't tell. There's supposed to be Dylan on this slide.
Yeah, we don't see Dylan. Oh, no,
okay. But there's a great quote of our song, 7 curses, 7 deaths should not kill him. If you integrate by parts 7 times using this differential operator, when you integrate up the exponential and differentiate that fraction with h over it, the arctangent just goes away after 7 times. And then you get something which is more elementary. And it's not straight, I wouldn't say not straightforward to do, but it's doable. I mean, in other words, if we spent a little more time, you can actually do the integral at that point. So this is now a method to compute the integral. It relies on this crazy sevenfold integration by parts, but that itself was motivated by the form of the answer. So that it wasn't like I was listening to Dylan songs and just came up with ideas for integrals. Maybe that's a good idea though. Anyhow, then the last question is, what about the vanishing? And so I spent way too much time thinking about this question, but it's very interesting that here's a definition. You take some arithmetic function with divisor functions, like sigma 2m is sum of the squares of the divisors of an integer m. And the statement is that this sum, I think I left out some people from the conjecture, but that sum vanishes when r is not 0. That seems to be a really non-trivial statement in number theory. So what I want to say is Danilo Radchenko, I've been working a lot with him, but I have to say all the ideas that have worked so far have been his, so I want to credit him. He has an argument that involves divergent series that if you just keep changing orders of things in a way that they don't converge and sum them around, he gives a pretty convincing argument that this is the case. And it's pretty remarkable. I mean, everything works out exactly that you get 0. So it's not like anyone has ever in physics used a divergent series argument, right? I mean, that just doesn't happen. So we're still trying hard to make this rigorous, but in a way, I think that's a pretty, if the conjecture came from physicists, I think it's okay to solve it this way. So let me just finish by saying happy birthday to Michael, and wherever you are blowing out candles, I hope you have many paper plates like you do here to share with us.
Thanks a lot, Steve, for that very nice talk. I mean, there are some hiccups, but it worked very well. This is what happens when you have an online workshop. So thanks a lot. I think what we will do is that we actually we want to try to stick to the schedule. So I would propose that we postpone questions for Steve until the discussion session, if Steve is able to be there for a little while at the end of today's session. So after Jens Funke's talk, we have this discussion session, and then you can try to find Steve in one of the breakout rooms and ask him some questions. So thanks again, Steve, for this very nice talk. And then if you can stop sharing your screen and
I'm just going to turn off the computer, I think, because that's all I can do. It just
to
relies on me to do that, huh? Uh-oh.
Yeah.
Maybe I can quit.
You don't have.
I'm just gonna turn off my computer. I'll try and turn it off.
Okay.
If you could eject me from the meeting somehow.
No, but now it's fine. Now you stopped sharing. So now Akshay should be able to share his screen.
Okay.
And it's now my pleasure to introduce Professor Jens Funke from Durham University, who will speak about theta series and singular theta functions.
Thank you, Sol, for the kind introduction, and thank you to the organizers for inviting me to this workshop. It's currently exam season in the UK, and for all you have been involved in this in one way or the other at some point in your life, you know what kind of administrative nightmare this is, and I'm delighted to be able to escape, at least for a little bit at this point. I mean, Stephen mentioned his 3 kids and the pediatrician. I rather would like to deal with this than with exam administration. All right. So first, I would like to review a little bit positive definite theta series, and we start very, very classically and in a certain sense remain classical throughout the talk. So in the setup, V over Q is my quadratic space of dimension M, and you can assume M is even, you don't have to. In the previous talk, it was mentioned that if you don't assume this, then you have to go work with a metaplectic cover, which I would like to ignore for this talk. The quadratic form is 1/2 of the bilinear form. Q of X, and L is a lattice. So, and even means that it's contained in the dual lattice. And the evenness means that in fact it takes values, the quadratic form takes values in the integers, and the evenness of course comes from the fact that we divide here by 2. And with this data, we have the very classical result, which I here now attribute to Hector Schöneberg. Of course, it even goes back to Jacobi, the 19th century, that if V is positive definite, then the associated theta series formed by you sum over your lattice, and you look at e to the 2 pi I q of x tau, and you look at this as, or you form this into the generating series, where the Fourier coefficients are the representation numbers, how often the lattice L and the quadratic form Q take the value n, that this forms a modular form of weight m over 2 for some congruent subgroup of SL2Z, which I won't say anything about today. This is very much an Archimedean talk. The data at the other local places will go along for the ride. And slightly contrary to the conventions of the previous talks, my upper half plane variable is always tau, but Q is Q e to the 2 pi I tau. And of course, the analytic theory of quadratic form, as Hector would put it, of course, has used this principle to great success for quite many applications about the study the arithmetic of these objects, particularly the representation numbers, and so and forth. We can play this slightly more general, namely, if you take P, a harmonic polynomial, homogeneous and harmonic of degree L on your space V, and then you form the associated theta series in a similar way, then this function is also modular, in fact, a cusp form, and the weight has gone up by L. And we're still with the same congruent subgroup gamma prime. And for the proof idea in its, if you want to, most concrete incarnation, we're using harmonic analysis. Namely, the function p of x times the Gaussian is an eigenfunction under the Fourier transform, and then you apply Poisson summation, and what exactly the congruent subgroup is, this does depend on your choice of the level of the lattice L, which is not of our concern today. And we can turn this was also mentioned in the talks earlier this afternoon, into a bit more representation theoretic background. Namely, we consider omega the Weyl or oscillator representations. So if I now know how to spell oscillator, I can, the oscillator representation of the dual pair of the orthogonal group of V times SO2R. Here I cheat if M is odd. And I use the incarnation of the Weyl representation acting on the Schwartz space of V, or, oops, if you want to do this slightly more general, on the L2 functions on V. And then you have the basic principle that whenever you have a Schwartz function, which is an eigenfunction under SO2, sitting inside SO2R under the Weyl representation, say of weight K, then you can form your theta series, bringing in your variable tau into this, and then this becomes modular of weight K for some congruent subgroup gamma prime. And basically the proof works along the same way. And there is, in general, even in the way how I form this here is, in general, this theta series might not be holomorphic. For this, you need to wonder whether it's a lowest wave vector. Under omega, so under 4SR2. And of course, the wave representation exists at all primes. And so we have the Schwarz-Boer functions here, or at the finite adels. Then of course the choice of the Schwarz function of the finite spaces is really the choice of the lattice L. Or if you really want to do this representation theoretic in terms of automorphic representations, you go to the adels. But we don't need to worry about this today. Now, today it's rather all about what happens if V is indefinite. So I take my signature to be indefinite, P comma Q, and P plus Q is M, the dimension. So in particular, my quadratic form better be non-degenerate. And if you form the naive theta series from above here, you're running immediately into problems. This wouldn't converge as Q of X takes negative values. And if you start with this expression here with the representation numbers, that wouldn't work either, because the representation numbers are infinite. So we have to worry about, so things are more complicated or more interesting in that setting. And however, I would like to give you one example, which I believe Don is in the audience, of course, in particular, been championed by Don Zagier as an example for an indefinite theta series, which you all know, and very well, namely the very classical Eisenstein series for SL2Z of weight, at least K, and of course even. And the Fourier expansion here is, of course, the Bernoulli number as the constant coefficient. And then we have here the quadratic form x times y, which is signature 1, 1. For my lattice, I take z squared. And if you want to, of course, this is a harmonic polynomial. Harmonic polynomial, and how do we get around the convergence problems? Well, I restrict to the positive cone. Namely, oops, this was not what I wanted to draw. Summation is restricted to the positive cone. And if you really, really wanted to, you could prove the modularity of the Eisenstein series in this way. Namely, you define the appropriate, well, I guess here L2 for the appropriate functions on your space, x to the k minus 1 times the indefinite Gaussian, together with the positive cone condition, and show by brute force that this gives you an eigenfunction under the Fourier transform. Maybe you don't want to do this, but in theory, one could. More conceptually, Siegel developed a much more general theory of theta series, at least of indefinite theta series. He was the first. So for this, he considered the orthogonal group of my quadratic space, and I'm looking at the connected component of the identity there. So that's SOPQ dot and the maximal compact subgroup K, SOP times SOQ. And suppose for everybody, this associated symmetric space G mod Q is very familiar. Familiar in particular for signatures, where one of the numbers is 1, 2, or 3. And what we will use is that this is also the Grassmannian of negative Q-planes. So all the subspaces of V which have dimension Q and on which the bilinear form is negative definite. G acts on this set transitively, and one given one is stabilized by a maximal compact subgroup. We can associate it to this a majorant, namely a minimal majorant. And I'm also proud to see is that I do believe Rainer Schulze-Pilot is in the audience, who ages ago actually taught me this and in lectures at the University of Cologne. So you can associate your majorant to this a positive definite quadratic form in the usual way. So if X is negative, is a negative definite subspace, you take minus of it. And if it's in the orthogonal complement, you leave the form alone. So, and this of course then defines the quadratic form everywhere. We take gamma, a stabilizer in our still even lattice, and we look at the locally symmetric space, D mod gamma. We might want to assume gamma is neat, but we don't have to. In any case, we have here some very nice collection of objects. And of course, you all know that for 2,1, D is the upper half plane. X is either a modular or Shimura curve. P,1, we're getting hyperbolic P space. And in general, for P,2, D is Hermitian. And here I write down, really going back to Siegel, the so-called Gaussian, namely the function phi0 x, also depending on z, writing e to the minus 2 pi q sub z of x. And note this is of course not positive definite. Given x, it's a Schwartz function. It has weight p minus q under the Weyl representation. And again, the principle I outlined before applies. I mean, here I write this down in painful details, what actually the associated theta series is. The important here aspect is that now we have a function 2 variable in the tau variable. It's modular, but non-holomorphic of the weight p minus q over 2. And in Z, it's a C infinity function on X. And the proof idea is really the same principle as what we had before. And we can play this for any Schwartz function or L2 function of weight L under the Weyl representation, and then we get in generally some non-holomorphic modular form on gamma prime. You do have to worry about a little bit about whether Poisson summation applies or not. And of course, this was also mentioned in Angesh's talk before, that then we have the theta correspondence here in its, if you want to, most concrete incarnation. You can use the theta function as an integral kernel in the orthogonal variable or in the symplectic, in the SO2 variables, and you get a correspondence, the theta correspondence of automorphic forms between SO2 and the orthogonal groups. And here in this way, not realized by House quotient correspondence, but rather by the integral correspondence using the theta series in an integral kernel. And of course, this goes back to, well, in this way, I'll formulate this for quite a long time. There is, of course, Shintani and Neva in the mid-70s who realized the Shimura correspondence between integral weight and half integral weight modular forms in this way. Valls-Bourget looked at this in detail from the representation theoretic correspondence. And here I put some more names, and I apologize for everybody who's not on this, is in the audience, but not on this list. All right. So, but I rather don't want to look at the automorphic representation properties of the theta correspondence, but rather I'm more interested in the geometry of this situation. Namely, how can we study the geometry of X, or the cohomology either of the group gamma, or depending on what your flavor is, or of the symmetric space X, which of course amounts to the same thing. And one of the nice aspects here, geometric aspects, is that we have a very nice set of submanifolds, or at least cycles, in our locally symmetric space X. Namely, if you take your vector X of positive length, you get the cycle D sub X, which consists of all these negative Q planes, which are perpendicular to X. So Z needs to lie in X perp, which is really a subsymmetric space for the signature P-1, Q, which hence the dimension goes down by Q. And that sits, of course, naturally inside D. So this is really a way of embedding the smaller symmetric space into the larger symmetric space, depending on your vector X. If you look at gamma X, the stabilizer, this acts on this. If you look at the quotient, and this maps not necessarily injectively into, but it's still an immersion into your locally symmetric space, so you get your cycles. You can look at all the vectors of length n in your lattice. This is still infinite, but by Siegel, essentially the finiteness of class numbers, mod gamma, this becomes finite. And then you look at the collections of all these submanifolds now indexed by a positive integer n. So n is here just a positive integer. And where does this lie? Just to space. So these are codimension Q cycles. In general, there might be with boundary as the same thing as X might have a boundary. But there are some of those, so this is defined over Z. And if we do this for signature 1, 2, well, then Zn are CM points, or if you want to Hegner points. So quadratic irrationalities in the upper half plane. For P, 2, so these have then codimension 1. Complex codimension 1. and some people call them Hegner cycles. I am not doing justice to the word Hegner here. Hegner cycles, or divisors, or special divisors, and so on. For 2,1, we're still, of course, the symmetric space is the upper half plane, but in that case, we get geodesics. And here, of course, we get hypersurfaces for a general hyperbolic space. So we get a very nice and very general collections of spaces and submanifolds. And the result of Kuttler-Milson is that, which is really the analog of what was happening in the positive definite case, is if you look at the generating series of these cycles in cohomology, then this becomes a holomorphic, an honestly Gauss modular form of the weight m/2, some subgroup. And where does this take value? Well, in the Qt cohomology. Meaning, whenever you apply a functional on the cohomology, you're getting an honestly Gauss scalar valued modular form. So for example, if you take a closed differential form here of the defining some class in Devam cohomology, you can integrate your differential form over the cycle, and you look at the generating series, and you get a modular form. And I should certainly mention here that the mother of all results of this type is the result by Hirzbo-Zagier for Hilbert modular surfaces of signature 2,2. And the proof idea is that they explicitly form a theta series. And in fact, it's a co-cycle. What it really is, it's they construct a co-cycle, a cube co-cycle in the relatively algebra cohomology with values in the wave representation. And more explicitly formulated, this is a Schwartz function, which takes values in the, these are the closed Q forms. And it has weight under the wave representation of weight of m/2. You form your theta series, which you can because you have this weight, and you get something modular. And in fact, if you then look at this in cohomology, then this becomes exactly the generating series of these cycles, where of course here I happily omitted all the nasty details involved in this. And I'm not going to explain what the cycle would be for n equals to 0 either. But one aspect is actually important or amusing in this proof is, so I have this theta series, which in general I said was not holomorphic in tau, but here in cohomology, it becomes holomorphic in tau, it becomes a modular form. So is it already holomorphic in tau as a differential form on Z? And the answer is no. Only after you take cohomology. And this gives and since we're going to need this later, we'd like to give you actually the proof of this. You know, every talk needs a little bit of a proof. And the proof goes as follows. They construct another form, Schwartz form, of 1 degree less, and the weight is 2 lower, such that if you apply the exterior differential in Z oops, that's the wrong variable. You get a Q form on the left. Then this is the same as if you apply the lowering operator in tau there. So you have this partial differential equation relating the orthogonal, the symplectic and the orthogonal variable in there is, and of course, Sol, the other Monday actually looked in your thesis, and I did see already some of these differential operator places already occurring there as well. For signature, was it 3,1 or 1,3? Either one. And what that really here happening is there is a certain double complex going, namely D and the del bar complex going. So we're really doing some calculation here in the spectral sequence of this. So that's really what was really behind this phenomenon here. And then the consequences is that if you pair your theta series against a closed differential form, this becomes holomorphic and then becomes the generating series of the cycle. And I cannot resist giving you the proof. So we do need that this is better be zero if you apply del bar tau. Well, we can pull this in because it's in the other variable. It's in there. But by the equation here, I can move this. Well, first of all, I can move it in here. And then, of course, I can apply this here. So therefore, what I have here is that then this becomes psi of q minus 1d. Ada is, of course, closed. So I can apply Stokes theorem. I'm over here. And now I declare victory because Ada was compactly supported. So the boundary value is zero, even if you're in the non-compact case. So it's a beautiful dance of differential of the differential operators. Or another way of saying this is if you look at phi q in the relative Lie algebra complex as viewing this as an SL2R representation, phi q is a lowest weight vector. I can't resist, because the non-trivial local systems were mentioned earlier this afternoon, that one can generalize this, and I did this with John Milson, to non-trivial coefficient system in quite great generality. So much for the background. I'd rather want to talk about the construction of Green's functions in singular theta lift. And I will restrict here, at least for the moment, to the orthogonal group OP, 2, or if you like 2, P better, that's of course fine as well. So V was my quadratic space of that signature. Dimension is P+2, which is M. I have my Hermitian symmetric space D, and the complex dimension is P. I have my lattice, I have the stabilizer, and I have my my space X, which here is by result of Bailey-Borel an algebraic, a quasi-projective algebraic variety. I have the cycles, which have complex codimension 1 on the symmetric space, on the locally symmetric space, or if I use them with the integers, parameterize them by the integers z of n. So just as a review. And I mentioned here before the equation here. In fact, here, in that case, we can play we can go slightly more general about this and namely, if we take phi2, which was the Kuttner-Milson-Schwarz function, which is a 1-1 form, Schwarz function, and phi0, the Gaussian, one has weight m over 2, the other has m over 2 minus 2, that then we have the equation which we had before, but now one step further. It's del z in phi0. This is now in a 2 form in z, that this is the same as del bar tau, so del bar in the tau variable for phi2. It's the same equation. Since I have here now the additional information of a Hermitian space, I have more differential operators. It's not only, if you want to del exact, it's del bar exact. And it's actually quite nice calculation in the real representation to check this by hand. And I will refer to this later on as the Milson equation, as John has in particular the champion of this way of looking at these things. So I have these objects, the Schwarz function with values in the differential forms and the Gaussian, and now I can play with this. And the first thing is you can form what I call the Green's function of Kuttler type. And in that case, actually, Steve constructed it on the nose. And namely, what you do is what that really is, you undo the tau bar here. You're looking at an antiderivative in tau. And for this, what you really do is what you can do is you look at the Gaussian and integrated it here. So you look at this integral. And this actually has singularities. In fact, logarithmic singularities. Along the cycle dx in D. But otherwise, it's a beautiful function. And at least formally, I can also view this as a function in tau. And I have undone the del bar in tau variable, at least formally, and this is justified by the theorem which independently Steve, Kuttler, and Jan Bonnier and myself proved is, if you look del bar of Xi, you get indeed the differential form in the Kuttler-Milson theory. And this is right on the nose as differential forms on D outside the cycle. And if you apply tau bar on it, you're getting back phi0. And that's what I meant with you're really undoing this equation here. You're integrating with respect tau, both sides here. And this is why it nicely works, except you pick up this singularity. And when you have these objects, you of course do want to wonder how does this work as a current? Is there a residue? And the answer is yes, and that's the current equation going back to Kuttler. So you take your test form, so P-1 form with compact support, and you take del bar of it, you get a top degree form, which you can integrate against the function. And what you get is, you get the integral of omega over the special cycle plus the integral of the two form, the non-singular two form against omega. And that's exactly the Green's equation. And that's the reason what it makes it a Green's function. It's not the standard one, but it beautifully works. And there exists a global version. I mean, I formulated this here for my convenience, only for on the symmetric space as well. You can do this by basically summing up both sides over all vectors of length n to lift this to the symmetric, to the quotient z of n. Question is, why do you want to do this? And Kuttler developed this vast program, the Kuttler program, we call it now, which is really the idea is of upgrading the modularity of the generating series of the special cycles from cohomology to arithmetic geometry to the arithmetic child groups, say, as developed by Gilly and Sully. But it's also quite handy to have this Green's function as a computational tool available in the theory of indefinite theta series. And let me just give an incomplete list of names who have thought about this in one way or the other recently or not so recently. I think it goes, of course, back to Zaghi, Zander-Svegas. Then a few years ago, Abramovich, Banjari, Manshot, and Piolin worked quite extensively exactly in the signature P,2 on this. Nazaroglu looked at the general signature. Steve then realized that one can do this in this theory. Martin Raum is also in the audience worried about this as well. And Steve and I wrote also a couple of papers on this as well. So as a computational tool, it's very, very handy as well. Now, so that's one way of constructing Green's functions to these objects. There's another way of doing this and this actually comes from theoretical physics originally. So, and to make my life simpler, let me call kappa p plus 2/2, k is the dual weight 2 minus kappa. And I let m here to be the space of weakly holomorphic modular forms, which are your regular holomorphic forms, except that you do allow for poles at infinity. And note, you better have to allow something here because typically your weight might be negative. And then Bonnier and I looked at an extension of those, namely what we call, now it's called are the weakly harmonic forms, which, as the name suggested, are harmonic. They have exponential growth at the cusps. And when you apply essentially del bar again, you end up in the dual weight 2 minus k. This is not positive typically. And you get a cusp form. So these are this kind of differential operators, which, of course, Stephen, not quite in this way, wondered about today, earlier this afternoon. And the result, in fact, is that the C operator here is surjective. You can get a primitive for all cusp forms in this way. And the kernel are, of course, the weakly holomorphic ones. what is more relevant for us now is that you can use this to construct singular theta lifts. So you take F, your weakly harmonic, your weak harmonic form, and you integrate this against the regular Gaussian theta function. And the point is that here the weight of the theta function is minus k. This has weight k. Together it has weight 0. You can integrate it against the Gaussian, and you're getting something which is invariant. And at the end, you're getting something on the orthogonal side. Of course, the problem is that this needs to be regularized. And in the process, you get singularities along cycles, or here the divisors, ZF, depending on your input function, but this is a finite linear combination of these ZNs. So, and this was originally proposed and carried out in great success by Harvey and Moore, and then picked up on the mathematics sides by Borchertz. And they looked at this when F is actually holomorphic or weakly holomorphic. And this then led to automorphic, or Borchertz products, as at least the mathematics people call them. And very, very roughly, you take phi and you can exponentiate phi to get an automorphic product, an infinite product. But then shortly afterwards, Bonnier and his collaborator, that was Ulf Kuhn and myself, in various incarnations, we looked at this when F is indeed not holomorphic, but harmonic. And the next thing is that, again, you satisfy the same set of the same current equation from before. Namely, if you look del bar of your current, so you integrate phi against del bar of your test form, you get the integral of your test form again over the cycle plus the standard error term. So it's again a Green's function. Yes, a Green's function. And what is this Green function? Well, that's what Bonnier and I determined, and what we refer to as duality, namely, well, up to some multiple of the Kähler form. Note, this is a function. You get a 1-1 form, so you can get your Kähler form, and then what you get is, well, you do want the theta function associated to phi2, tau and z, which is the 1-1 form, but you do need to get rid of the tau variable, and you're looking at the Peterson inner product of weight m/2, which is kappa. In weight kappa. This is the additive Borchertz lift. You take del bar, it becomes smooth, the logarithmic singularities go away. Get a multiple of the Kähler form times, take the Kuttler-Milson theta series, 1-1 form, modular in tau. You take F, turn it into a cusp form, take the Peterson inner product, and there you are. So, and that's how we were able to relate the singular theta lifts to the ones in, to the more classical ones, at least with the geometric interpretation. All right. And now you have two Green's function, namely the one of Kuttler type and then the one which arises from a singular theta lift. And you might want to compare them, which I won't go into this, but this was done by Ehlen and Sankaran. Essentially, if you look at the difference of them, form a certain generating series, you're getting something modular. And Oda Suzuki used similar constructions, well, constructed similar or related Green's function using entirely Lie theoretic methods. There is no theta pair there. All right, which raises the question, can we do this for other groups or other dual pairs? Say, for example, here we had OP2, if you want to, with SP. And well, usually I'm an SPN person, but let's call them SP2N here. This is, or you might as well think about unitary groups. Dual pair UNN, where then you would want to try to get Hermitian modular forms. And the theory I developed so far is only restricted to divisors. Can you do this for higher dimensional co-cycles? And the answer is yes, and that's what I would like to present today. And for this, we're going back. We're getting the color out. Namely, we look at this for the unitary group UPQ. So then V is now a Hermitian space. So you have your Hermitian form is, and the signature is actually quite general, P plus Q. So, and here, of course, you are not over over Q, but over, say, an imaginary quadratic field. And so the dimension I still call M, which is P plus Q. We still have the big unitary group. I can look at the quotient, which is now has dimension, complex dimension P times Q. And I can again realize this as the negative Q Grossmanian in V tensor R. I can still have my lattice, my stabilizer. I get my quasi-projective algebraic variety. I can get now, in the same way as before, my cycles. So these are the Z's in D, which are perpendicular to X as before. I get them in the quotient. I can sum them up, again, parameterized by positive integers. But now they're having codimension Q. Codimension Q, so they have higher codimension. I'm away from the divisor situation. And well, what do I have? I still have the Kuttler-Nielsen forms in these ones, which are now, let's call them phi QQs, because they in fact QQ forms on my symmetric space, which have no weight M. In the unitary group, you always double the weight. It's M, and we do have a form Xi, which is a Q minus 1 form now, which has weight 2 less. And this theorem is now due to Erik Hofmann and myself. So we still have these forms. We replace the Gaussian by the primitive for the equation there. And here I'm getting Q. So it's the same equation you can solve. Now in the different dual pair, you look at the geometric theta form. Before it was a 1-1 form on the orthogonal symmetric space. Now it's a QQ form on the unitary, in the unitary universe. And we still have this. So what underlying this is we really have the dual pair UPQ with U11. But of course, U11 is, and please forgive me that I'm forgetting this, essentially SL2. So on the other side, we still have SL2 to work with, and this becomes now quite crucial for what will happen in the following. Well, how do I now form a Green's function of Cutler type now? Okay, type. So that's again Eric with myself, where we replace the Gaussian, which was what we had here before for the big equation here, with the one which solves the equation here. We had the phi QQ God given. You can look at this. Can I solve this equation? Yes, I can. With I, and I take exactly this to the series. Again, we're getting, well, maybe since we're no longer talking device, it's not quite a logarithmic singularities along the cycles. And I again have the same package as before. If I, well, maybe let's label this using the size. If I look at this object now, which is a Q-1 form in the unitary symmetric space, I take DDZ, I get a Q, Q form. And what is it? Well, it is exactly what you hope it is. Phi Q, Phi Q. And if I apply del bar to it, I get Xi back. So the constructions so far were completely functorial. Or the decisive point was that you're able to solve this equation. You have this, you look at this, and then you need to solve this partial differential equation, which you can completely working in the Weyl representation. So, and then you have the current equation. Again, Eric self. So this all beautifully works as a charm. You get the test form, which now, however, is of higher codimension. So there's a Q here and a Q here. And what you're getting is, well, the same equation as before, still holds. You get the integral over the cycle plus the one coming from the KM forms, the error term, if you want. And there are various proofs. So this is, I prefer a very lead theoretic proof for this, and there are a global version again for this. So this works like a charm. And again, you can use this in a Cutler program, but it has not sufficiently explored this. I don't think anybody has so far looked at this these constructions in terms of constructing indefinite theta series for the unitary group. But then we can play the same game to define a singular theta lift, which now won't take values in the functions on the orthogonal symmetric space, but in the forms on the unitary symmetric space. So kappa now is m. Before that it was m over 2, so it's n here is, and the dual weight is, well, is 2 minus m. I still have the weakly holomorphic and the harmonic forms. I still have this. And I use the theta series associated to the auxiliary form xi, the one which solved the partial differential equation, to define your singular theta lifts. So if you want to, this is an axiomatic view of viewing singular theta lifts, is the proper kernel function for singular theta lifts is the one which solves up there the differential equation. You still have to regularize, you get singularities along the cycle ZF. Okay, here I have to say, well, since I'm no longer talking devices, we will not have automorphic products in this way unless, of course, Q is equal to 1. And that was in fact done by Eric Hoffman in his PhD thesis. But it hasn't been quite explored sufficiently what you can do on this side geometrically if you do put in something weakly holomorphic in the lift. So that's, again, some open question, not been done. And then we have the result. So again, Eric and myself is, so if I look at a P-1, P-1Q form, so high dimensional one is, then I get the same current equation as before. So I have this, I have the entire package again, and indeed, I get the duality result. I need to change some variable here. This one here, phi QQ. And here, you get an appropriate transform over there. So you're getting the same duality package again. This should already give rise to quite nice applications for, again, in arithmetic geometry and part of the Kutler program. But let me move away from this and rather wonder, now what? Further remarks?
John's,
Well,
we're at 45 after, so just try to keep a few more minutes if you can.
I'm done in 1 minute. Sorry. I thought
it's fine. Please, it's fine. Please finish. Take a few minutes just to warn you about the time.
I was doing great.
It's all good.
I still had 15 minutes. Oh God, sorry. Yes, one, and that is just 1 minute.
It's all good. Don't worry.
So, what about these higher dual pairs? Well, we do have a KM theory, and we can solve the Milson equation, which is the crucial differential equation, which I mentioned before, and we can do this in general. So that is on the representation theoretic side, no problem. And in fact, Garcia and Sankaran, using a different approach, rather using Quillen's theory, use this of the construction of green forms for higher codimension of the Kutler type, for higher codimension n in the orthogonal group or nq in the unitary case. it's still not quite open whether that's the same, whether it was what we have been doing, but it should be, and they use this quite nicely. The problem with singular theta lifts is that the naive input space of weak harmonic forms is empty. There's basically the Köcher principle in your way in the symplectic case for higher dimension. Brunier found a way of getting around this for real quadratic fields in the Hilbert modular case using so-called Whittaker forms. And that's roughly your usual Whittaker function. However, you look at the bad solution, the one which has exponential growth as you go out, and not the one which is nice and gives rise to Cus forms, to Poincare series, to Cus forms. And together with Jan and Steve, we upgraded this to the symplectic side with quite some analytic pain. Unfortunately, that's still not enough to get the singular theta lifts going. Just writing down an integral won't do, it's so unmanageable at this point. And so here, this is an AIM working group. So that's Jan Bonnier, myself, Steve Kutler, Siddharth Sankaran, and Tongha Yang. So we are currently trying to get this going with the input we have, with the Whittaker forms and all the other ideas. So, and that's work in progress. So sorry for going a bit over time, and thank you.
So let's thank you very much, Jans, and let's everybody please thank Jans. I'm going to turn off the recording now.